A commercial aircraft touches down at 270 kilometers per hour. The landing gear drops from 0 to that speed in less than 1 second. No spinning, no warm-up, just immediate, violent contact with concrete at highway speed. And the tires do not explode. Not today, not yesterday, not in the thousands of landings happening around the world right now. So what is actually inside an airplane tire that makes this possible? And why is it nothing like the tires on your car? Start with the numbers, because they are extraordinary. A typical tire on a passenger car is inflated to somewhere between 2.5 and 3.5 bar of pressure. That is roughly the pressure you would feel if you pressed your thumb hard against a surface. An airplane tire is inflated to approximately 14 bar. That is 4 to 5 times higher than a car tire. On a large commercial aircraft like the Boeing 747, each main landing gear tire carries roughly 25 tons of aircraft weight. There are typically 16 main gear tires on a 747, plus 2 nose gear tires. Each one of those tires must survive not just the weight, but the sudden rotational shock of going from stationary to 270 kilometers per hour in under a second. A car tire doing that would shred instantly. An airplane tire does not. The reason comes down to construction, material, and pressure, all working together in a way that took decades of engineering to perfect. The construction of an airplane tire looks nothing like a car tire from the inside. A car tire uses a radial construction. Layers of steel belts run perpendicular to the direction of travel, making it lightweight, comfortable, and good at absorbing road imperfections at moderate speeds and loads. An airplane tire uses a bias-ply construction. Multiple layers of nylon cord run diagonally across the tire at alternating angles, creating an interlocked structure that is stiffer, stronger, and far better at handling sudden extreme loads. The sidewalls are thick and rigid. The entire tire is built to resist deformation under shock loading, rather than absorb it gradually like a car tire would. The rubber compound itself is different. Aviation rubber is specifically formulated to handle the heat generated by that instantaneous spin-up on landing. When a tire goes from 0 to 270 kilometers per hour in a fraction of a second, the friction between rubber and runway generates an enormous amount of heat almost instantly. The smoke you see during landing is not the tires burning. It is the surface layer of rubber vaporizing as it absorbs the thermal shock of spin-up. The tire survives because the rubber underneath that thin, vaporized layer remains structurally intact. The heat is real, but it is brief and contained at the surface. The inflation gas inside an airplane tire is not air. This surprises most people. Car tires use regular air, which is roughly 78% nitrogen and 21% oxygen. Aircraft tires are inflated with pure nitrogen. The reason is safety and stability. Regular air contains moisture. At altitude, temperatures can drop to -50 or 60 degrees Celsius. That moisture freezes and expands inside the tire, creating unpredictable pressure fluctuations. On landing, the sudden heat spike from touchdown can make those fluctuations even more extreme. Pure nitrogen contains essentially no moisture. It is chemically inert, so it does not react with the tire's internal materials over time. Its pressure also remains far more stable across extreme temperature ranges, from the frozen air at cruising altitude to the heat of a hard landing. There is a secondary benefit. Oxygen supports combustion. In the unlikely event of a tire failure with enough heat to cause ignition, a nitrogen-filled tire is significantly less likely to catch fire than an air-filled one. Now let us talk about what happens during the landing roll itself, because the tires are doing something most passengers never think about. After touchdown and spin-up, the tires begin absorbing braking force from the carbon brake assemblies inside the wheel hubs. The brakes clamp down on the spinning wheels, converting kinetic energy into heat. The tires must transmit that braking force from the wheel hub to the runway surface without slipping, skidding, or deforming. The anti-lock braking system monitors wheel speed continuously and releases brake pressure the instant it detects an impending skid. But the tires themselves must maintain grip on the runway surface throughout this process, in all weather conditions, on wet or dry or contaminated surfaces, at speeds ranging from 270 kilometers per hour down to 0. The tread pattern on an airplane tire is designed specifically for this. Unlike a car tire with complex grooves for water dispersal at moderate speeds, an airplane tire has relatively simple circumferential grooves. At landing speeds, aquaplaning, where a layer of water lifts the tire off the surface, is the primary risk. The grooves channel water away from the contact patch fast enough to maintain rubber-to-runway contact even on a wet surface. One of the most remarkable things about airplane tires is how long they last, and the answer is not what most people expect. A single airplane tire lasts approximately 200 to 300 landings before it needs to be retreaded or replaced. That sounds low compared to a car tire, which might last 30,000 kilometers. But consider what each of those landings involves: a sudden impact load of 25 tons, an instantaneous spin-up from 0 to 270 kilometers per hour, braking forces of enormous magnitude, and heat spikes that vaporize the surface rubber layer every single time. After every flight, ground crews inspect the tires visually for cuts, bulges, and wear. They measure tread depth. They check inflation pressure. A tire that passes inspection after 200 landings has survived the equivalent stress of tens of thousands of car trips compressed into a fraction of the time. When a tire reaches the end of its service life, it is not discarded, it is retreaded. The worn outer rubber is buffed away, and new rubber is bonded to the existing carcass. This retreading process can be done multiple times on the same tire body before the carcass itself is retired. There is one scenario that tests airplane tires beyond their normal limits: a rejected takeoff. The aircraft is accelerating toward rotation speed, the point at which it must commit to flight. Something goes wrong. The pilots abort. At that moment, the full braking force of the aircraft is applied at maximum weight and near maximum speed. The tires must handle the combined shock of full braking force, the heat from the carbon brakes transferring into the wheel assembly, and the sustained high-speed load of decelerating a fully loaded aircraft from near rotation speed to 0. After a maximum energy rejected takeoff, the tires and brakes are so hot that the aircraft cannot be moved for up to 45 minutes. Thermal fuse plugs in the wheel rims are designed to melt and deflate the tires in a controlled way if temperatures exceed safe limits, preventing an explosive decompression that could damage the aircraft structure or injure ground crews. The tires do not need to survive this event in perfect condition. They just need to hold together long enough to stop the aircraft before the end of the runway. So how do airplane tires survive landing without exploding? They are inflated to 4 times the pressure of a car tire using pure nitrogen that stays stable from -60 degrees Celsius to the heat of a hard landing. They are built from bias-ply nylon layers that resist deformation under shock loads that would destroy any car tire instantly. The rubber compound is formulated specifically to vaporize at the surface while remaining structurally intact underneath. And every single tire is inspected after every single flight by crews whose job is to catch problems before they become failures. The smoke on landing is not a warning sign. It is the tire doing exactly what it was designed to do: absorbing the impossible so that 270 kilometers per hour becomes a routine stop.